Shall we continue, ma? I think it is already 18 people are there, so hope other people join. So good morning to everyone, 18 people. So let us start the today's discussion. Still a lot
Good
of
morning,
topics
sir.
are there. Yeah, yeah. Thank you. A lot of topics need to be covered. So in the last class, I think we are discussing about the problems of solving using the performance equations of PFR and MFR, right? We'll continue further. Still, a lot of problems are there. You please try to do the problems, exercise problems or worked out problems in Gavani, because I need to cover still a lot of topics. Next thing is we'll see the size comparison of single reactors. Single reactors. That is how much, what is the volume required for a single PFR or a single MFR and all, right? So let us see the mixed versus plug flow reactors for a first and second order. This order plays a very important role. It's not that always mixed reactor is better than plug flow reactor or plug flow reactor is better than mixed reactor. This order plays a very important role. Why the order plays a very important role? Because you are getting this RA. RA is nothing but K into Ca power n. If you are having Ca power 1 as a first order, you get one expression. If you are having a second order, Ca square, then if you do that integration, you get a different quantity. So based on that, this will be different. We'll see that, right? How we can compare the sizes. So let us compare by using, this is the, you take any reaction, nth order reaction, you are writing the disappearance, minus RA is minus 1 by V into dNA by dt, K into Ca power n. Let it be nth order kindly. Then we will substitute first and second order there. So where n ranges from any order from 0 to 3. Generally, the order of a reaction not more than 3 is practically found. Even 3 is very rare. The order of a reaction 3 itself is very rare. Very few reactions are having third order. More than the third order, generally in literatures also you will find very difficult to get it. Even 3 is very difficult. There are some reactions which are having 3. Generally, the order goes from 0 to 2 point something 2.5, 2.6 like that, right? So let us take n ranges from 0 to 3. So what is tau m? Tau m is nothing but V by V naught, correct? V by that is volumetric volume of the mixed reactor divided by volumetric flow rate. So what is tau m? V is Vm divided by tau. V by V naught, that is volumetric flow rate. Volumetric flow rate is nothing but Fa naught by C naught. So if you rearrange that, then Ca naught V by Fa naught, this is for m. M is nothing but a mixed reactor. That is equal to tau m is Ca naught Xa by minus Ra, because tau by Ca naught is Xa by minus Ra is the performance equation for a mixed reactor. Tau m you are writing like this. So you can write like this. Whereas Ra is nothing but K into Ca naught power n minus 1, because Ca naught is here. So Ca naught will come here, n, Ca naught power n it will come. So 1, if you take n minus 1 we get into Xa divided by, for a first order, yeah, 1 minus Xa power n. So if you are taking a exponential, because this you can write for both liquid phase and gas phase. Let us write for a gas phase where expansion factor also come into picture. That it will be down. So if you rearrange, it will goes up, n power n. So if it is a liquid phase reaction, you can simply say substitute this epsilon A is 0 and then you can finish off, right? So we can write for plug flow also. Plug flow is tau p, is nothing but the p. The suffix is the reactor, m for a mix and p for plug flow. Again, CA naught V by FA naught. This is the tau P. If you know CA naught, FA naught, and V, we can calculate tau P is nothing but again CA naught because tau by CA naught, right? Integral 0 to XA dXA by minus RA. Minus RA, you substitute K into CA power N. CA, you substitute as CA naught into 1 minus XA. So you are having one CA naught here. You are having CA naught power N. So if you take down CA naught power N minus 1, this you are taking the outside the integral because it is constant. So integral 0 to XA. Again, you are writing for expansion 1 plus epsilon A XA whole power N dXA by 1 minus XA whole power N. Correct? Any doubt in writing these two? I'm just writing for both liquid phase and gas phase reactions. I want to compare the what do you call mixed flow and plugged flow in the same curve, right? This is for nth order kinetics, right? So if you divide one over the other, what will happen? Tau P, tau M by tau P. So you can see here, tau CA naught, this particular thing you can take out this side or whatever you want. So KK gets cancelled out. If you divide one over the other, KK gets cancelled out. And tau M CA naught power 1 minus N, it comes here. By tau CA naught power 1 minus N P is, so you are comparing the taus of both the mixed and plug flow. That is nothing but you can write these two also, one over the other. CA naught power N V divided by FA naught M. CA naught power N V by FA naught power P. So don't try to strike out these two, right? Because this is for flow rate for M and this is the flow rate for P. If it both are same, then you can strike out, right? But unless otherwise it is mentioned, don't strike out. Is this particular thing, XA 1 plus epsilon A XA by 1 minus XA whole power N. This is for M, that is the mixed flow. This is for the plug flow, right? We can still refine it. Now substitute that epsilon A is going to be 0. You are consider only for gas phase, liquid phase reactions. What will happen? So that's what, with a constant density, your epsilon A will go to 0. Therefore, you are left with tau CA naught power N minus 1 divided by tau CA naught power N minus 1 P is, you can put this also. Let us put this. This is going to be 0. Then this will be 0. So you are left with XA by 1 minus XA whole power N, right? XA by 1 minus XA. This entire thing is going to be 1. 1 power N is 1. Therefore, XA by 1 minus XA whole power N, that is for M, divided by, now this is going to be 0. Then you are left with 1 by 1 minus XA integral. 1 by 1 minus XA integral is this 1 minus XA whole power 1 minus N minus 1 by N minus 1. And if you substitute the limits, you get this, right? This is nothing but 1 by 1 minus XA dXA, right? So substitute the limits. Then you get this, right? This is applicable when N is not equal to 1. When N is equal to 1, then when the order is equal to 1, this becomes 0. 1 minus 1 becomes 0, though 1 minus XA, entire thing will become as 1. 1 minus 1 will be 0. So anything by 0 is infinite. So this equation is not valid when there is an order of 1. That's an important thing for an order 1, right? So if you still refine it, this tau CA naught N minus 1 M divided by tau CA naught N minus 1 P. This is nothing but XA by 1 minus XA. If N is equal to 1, this is for N not equal to 1. Any order other than N is 1 here. If N is equal to 1, then what will happen? N is 1. Therefore, XA by 1 minus XA divided by this particular thing, N is 1. Therefore, 1 minus XA becomes 1 minus 1, 0. So this becomes 0, 1 minus 1. So you are left with integral. Then you can put it as minus ln ln 1 minus XA P. So it's understandable, right? This particular thing, it comes for a first order, and this come for a plug flow, right? Now, these two, what we do is, we try to put on a graph. We'll try to put on a graph. Now, this is the graph. This I am putting with 1 minus XA because both sides it is 1 minus XA is there. 1 minus XA on the x-axis and tau CA naught n minus 1 for a mix divided by tau CA naught minus 1 for a plug, or if you know a CA naught V and a FA naught, you can compare that also. Either it is in terms of taus or CA naught. Now you will see either this graph you are putting for n is not equal to 1, n is equal to 1, or you can put this itself. You can put this itself. This itself will give you for expansion also. Let us see without expansion what is going to happen. This is 1 minus XA. 1 minus XA. If XA is 1, if XA is 0, let us assume XA is 0. XA is 0 means the value is 1. This, right? So your graph is starting from here, right? Your graph is starting from here because if XA is 0 at a starting of the reaction, 1 minus 1, 1 minus 0 becomes 1, right? The maximum value of it is 1. Now, if XA is fully converted, XA becomes 1, right? XA becomes 1. So 1 minus 1 will be 0. So your graph is going from this side because you are putting the thing for 1 minus XA. So it goes from here. Now you see, let us see the solid lines first, then the dotted lines. Now this you are putting for 1 minus XA. As the order is going to change, you are having the order of 0.5, 0.25, 0.5, minus orders, and again positive orders. Now you see here, this order, what is this? This order is 0. If the order is 0, you are getting a solid line, right? Again, what is this order? You can see this order is the first order. This is the first order, right? Order 1. So this is for the second order. This is for the first order. So you can see clearly as the order is increased, what is happening? Your curve is shifting towards this. Your curve is shifting towards this means for the same particular tau value, let it be tau is 10. So for tau 10, for a particular, what do you call this, mix for a first order reaction, you can just project it down. Then you are left with 1 minus XA as around some value. From that you can calculate what is the XA value. So this is nothing but the ratio. This is the ratio of that particular thing, right? So you can see here as again it increases the same order, you can see the curve is shifting towards this. It's not only with the order, even with all the solid lines is with the order. This is order 0.5. This is order 0.25. Now let us take the order as 1. If the order is going to be 1, this is the expression. In this expression, if you substitute or you take this expression, you put order 1 and you put epsilon A as 0 or epsilon A as 1. So you change your epsilon A from minus 2 to plus 2, minus 2, minus 1, 0, 1, 2. So 5 values you can take. So based on that, if you see here, this is order 0, second order where epsilon A is 0. As the epsilon A is positive, you can see your curve is shifting towards this, all the dotted lines. If the epsilon A is negative, this is positive. Positive in the sense you are getting more number of moles, that is expansion in moles, like A gives some 4R like that. There can be 2A gives R where the number of moles is decreased. Then what will happen? Your epsilon A becomes negative. If there is a negative, then you can see the curve is shifting towards this side. This happens same even for the second order also. You can see the solid line where epsilon A is 0. For a positive order, you get towards this side, and negative order towards get downside. Right? So your ratio of the tau piece that for a mixed reactor by plug flow reactor not only changes with order, even it changes with the amount of the expansion. It changes with the amount of the expansion, right? So that is what this curve will give you. I'll just equate some points. Now you see, for any particular duty, for all positive orders, you can see all the positive orders. For any particular duty, your mixed reactor is always having more tau p or more volume than that of plug flow reactor. That is one particular thing which you will get. For any particular duty, these 3 points are very important. Lot of 2 marks will come in this. For any particular duty, for all positive orders, the mixed reactor is always larger than the plug flow reactor, or the volume, the ratio of the volume increases with the reaction order. That is what we saw here. The ratio is increasing as with the order, and the ratio is decreasing if the order is decreased. You can see the slope. It's going much steeper, right? That is the first one. The second one is when the conversion is small. When will happen when the conversion is small? When the conversion is almost 0, then your value becomes 1. Yet particular 1, almost order is not having any role to play, because almost it is starting. That is what. The reactor performance is only slightly affected by the flow rate. Either if the conversion is small, either a plug flow reactor or a mixed reactor, it won't, your conversion won't depend on or the performance won't depend on this flow type. The performance ratio increases very rapidly at a higher conversion. What is higher conversion? Higher conversion is nothing but XA is 1. When XA is 1, your value is 0. That means here you can see large variation. Whereas when XA is small, your value is 1. Here you can see less variation. So what does that mean is, when the conversion is small, either a plug flow reactor or a mixed reactor, you will not have much difference. But when the difference of that plug flow reactor and a mixed reactor, especially the conversion, will vary when you are attaining, where you are going for a higher conversion. That is one more very important point which you get from this curve, right? So I'll repeat again. When the conversion is small, the reactor performance is only slightly affected by the flow. The performance ratio increases very rapidly at higher conversion. Consequently, a proper representation of the flow becomes very important in this range of conversions. So here again, I tell you, you may think that this is higher conversion and this is low conversion. It is wrong. 1 minus XA I am talking. So if XA is high, your value becomes less. So at a higher conversion, your value becomes here. At a lower conversion, your value becomes this. So that keep remembering it, right? When you are reading the points. Otherwise, you get confused with generally we write a curve. This will be the lower value and this will be the higher value. But here, as you substitute the higher value, then your value becomes less. If you substitute lower value, the value becomes more, right? That's you remember, right? The third one is the density variation affects during the reaction design. However, it is normally of a secondary importance compared to that of the types of flow. Now you see here, the density variation is also from 0 to 2 to plus 2 or minus 2. We're basing this as a base. Either it goes up or down, but the variation is very small. You can see the variation of that dotted lines. It is very small around this thicker line. Whereas the variation in this particular pattern is huge, right? That's what he's giving you. What do you call that? Compression plays a very important role, but very less range. Now you can see the third order also. It starts much higher, right? That 3 points are very important. These 3 points are very important for any particular duty or any particular positive orders. Again, I keep that point in mind. All positive orders, the order can be negative also. For a negative order, it will be ulta. That is, your plug flow reactor may have more volume than a plug flow mixed reactor. That we'll see a bit later. But for all a positive order in the sense it is greater than 0. Even 0.2, 0.1, 0.5, all the orders. Any positive order, your mixed reactor always will have more volume or more tau they compared to that of tau p. That is plug flow reactor. This is the question I asked, why? Okay, I'm showing you all this curve and everything, but why? why there will be tau p is more or volume of a reactor for a mixed reactor for a particular conversion for a mixed reactor will be very high. That's what I asked. Some of you, I think Arjun, I think they sent one mail. Yeah, Arjun, go ahead. What you talked, just we'll finish off here itself. Yeah, why mixed reactor will be higher volume than plug flow reactor? You're there, Arjun? Yeah, go ahead.
Yes, sir.
Yeah.
So because in the mixed flow reactor, the molecules will follow different path lanes. Some may follow a large path lane and some may follow a small path lane. So it may happen that some molecules which got converted also stays in the reactor for a long time, and some molecules which didn't got converted, it may go fast from the reactor outside. So the conversion may be less for the mixed flow reactor for same volume than the plug flow reactor. So if we want to increase that conversion, we will increase the number of molecules that we are sending for the reaction. So that's why the volume of that reactor also increases due to the extra molecules that we have added. So that for a same volume, conversion will be different. So that's how, sir.
Yeah, good. All people understood what Arjun told. Arjun is telling that in a mixed reactor, since it is going out, so any molecule can immediately go out, or some molecule can stay inside for a longer period of time. Whereas in a plug flow reactor, it goes in a tube. So that fluid once go out only, the other fluid will go in. Therefore, in that process, your what do you call that volume required for a plug flow reactor is much lesser. That is what he is claiming. Correct, Arjun? Arjun?
So yes, sir.
But
Because the
I again
molecules.
ask one more doubt to you. Why you increase the flow rate? The let you keep the flow rate constant. Now you talk with the flow rate constant. You are not increasing the flow rate. You are telling that flow rate is increasing. That is, you are making the flow rate to increase so that the entire molecule will have some time inside. That's what you are claiming in a mixed reactor. Correct?
Not actually flow rate, sir, but if we increase the volume,
Molecule.
we can have more molecules in that reactor.
But again, if you increase the volume, also same thing will happen, right? Some molecule can go out, right? Anytime because it is continuously going out.
Yeah, it may go out, sir. But like if I send 10 molecules in MFR and
Hmm.
only 8 are getting converted, now
Hmm.
I am increasing the 10 molecules to 14 molecules. Now
Why?
10
Why?
will
Why?
get
That is
converted.
what I am telling you. That molecule is constant. I am not increasing that. You keep the molecule constant and then talk. If you are increasing here, again in plug flow also you have to increase. Then it makes the same. 10 molecules comparison or 14 molecule comparison is going to be same. That's what I'm just claiming you. You understood
Okay.
what I asked?
Yes,
Why
sir.
you are increasing from 10 to 14? You compare with 10. So that means that you
Yes.
somewhere there is a mistake in what you are assuming. Correct? Yeah,
Yes.
I agree. I appreciate his effort. At least some different answer he gave, but that is not the true. That point it will come when we go for fourth unit, right? That I will. That's why I'm not revealing the answer. That is absolutely correct what Arjun told, but that answer is not for this answer. That answer is for some other, something else. Like what is what do you call non-idealities which are present inside the reactor. That answer is for that, not for this. This answer is not correct, Arjun. What you gave. But I appreciate your effort. Really, that point is good, what you told. But here I'm trying to make the volume, what do you call, flow rate and everything constant. I'm not increasing the number of moles to compensate or something like that. Okay. Hmm? We'll
Okay, sir.
you try to still debug, right? I'll give you some more time because this point is very important. That point I'll tell you when I go for a third unit, not now, because that point is required for me to talk third unit. Why a mixed reactor is bad compared to that of plug flow reactor? Because if I didn't tell that point, then the entire third unit I cannot cover. The moment I tell that point, the entire third unit is covered. That's why I just try to hold for some more time. In the meanwhile, you can give the answers, then we can discuss. Good point as he told. All right. Okay, let us go for the next one. Uh, Now for a first order reaction, because we are trying to compare the first order and second order. For a first order reaction, K tau is the Damkohler number. Whereas for a second order reactor, your CA naught will also come into picture. That is what we earlier showed. Now, what will happen if there is a second order reaction, like A plus B gives a product, where M is CB naught by CA naught, and RB is K into CACB. Either the order can be like this, or order can be like this also, KCA square, where your CACB is almost 1. So both are in equal. So otherwise, what will happen is some B maybe exists, and you're trying to find out only a limiting reactant where it's A. So when a large excess of B is used, then its concentration is appreciably not changed, either final concentration or initial concentration, because only the limiting reactant is what the conversion you're bothered, where the concentration there will be a changes. So that time also you get KCA square, where CB can be safely neglected. If this particular B is going to be excess, then either you can put in terms of second order, or even you can put in terms of a first order also. That's up to you. Right. So that also you can compare. Any comparison, if you are giving minus RA with the XA, your area of a rectangle is what is the CSTR, and the area under the curve is what is your plug flow reactor. From this, we can clearly tell that for any positive orders, your area required, or the tau is nothing but the space time, or the volume requirement, tau by CA naught, or V by FA naught, anything, right? That is, mixed reactor is much higher. It requires much larger volume than the plug flow reactor, right? This is the graphical comparison. In this graphical comparison, you can find out, but why it is like that? That is what my question, right? So let us see now. This is only you are comparing one order, one reactor at a time, right? In general, in process industries, you can have multiple reactors, not like multiple reactions. Don't get confused with multiple reactors and reactions. Multiple reactions are like series and parallel reactions. Like A gives R gives S, or A is giving R and A is giving S. That kind of things you can compare, or you can have some 2 or 3 reactors in series, or 2 or 3 reactors in parallel. For one reactor itself, for a reactor, a particular reaction, you are having a variation in plug flow and mixed reactors. If you combine both for a single reaction, A gives R, you can combine instead of one reactor, instead of one big reactor, you can have 2 small reactors, either PFRs in series, or CSTRs in series, or PFR and CSTR in series. Before itself, I reveal what I'm going to do, just like Bahubali giving the before itself that Bahubali, what do you call that? Katappa killed Bahubali, right? So there is no suspense. So that suspense should be revealed there. Otherwise, you won't have that interest. So here itself, I'm revealing you, instead of one reactor, if you are having a combination of reactors, if you want to have 90% conversion, let you assume that you want 90% conversion. If you want to have a 90% conversion, let you assume that 80 liters of plug flow reactor or 100 liters of mixed reactor is required, because mixed reactor is having more volume, right? So for a 80% conversion, let you assume, I'll just try to put here so that I can make that thing clear. Just 1 second. Pointer, pen, yeah. Now you see, I want to have I want to have 80% conversion. For this, I require VM as 100 liters. This is all some assumptions, right? This is all some example, right? For an example, I'm giving. PP, that is volume of a plug flow, let it be 80 liters, right? For the same conversion, if you keep one reactor, your volume of CSTR is 100 liters is required. And if you use a plug flow reactor for the same conversion, you require let it be 80 liters. Now the same conversion I can attain with one CSTR and a PFR in series. So what I do is the outlet will go as an inlet to this and then this particular thing. So if I have this combination, or you can have one PFR first. You can have one PFR. This is goes in and this is coming out. This we can send to a one more MFR. This is the inlet to it, and this is the outlet. So instead of one big reactors, you can keep one CSTR and one PFR, or one PFR and one CSTR, or two what do you call PFRs in series. You can put two PFRs in series. What else combination will come? Yeah, I think I am not getting this. Yeah, or two mixed reactors in series, again going out and coming out. This is the inlet. The outlet goes to the inlet to the next one and then coming out. So this is the first combination. This is the second combination. You can have third combination, four combinations, because there are two cases. So four different combinations you can have. In all the four cases, if your conversion is same, the volume required for this, or for this, it can change. It can change. So you can get this same 80% conversion. Here you are using 80 liters, right? Here you are using 100 liters. So if you use this particular thing or this particular thing, what will happen is your volume required for both the reactors will be much lesser than this 80%. That is 80 liters is what you are climbing. This is the best, right? Compared to this, much better than this is there by combining reactors in series, either this or this, sorry, or this or this, or you go one more, one big reactor and one small reactor, again one plug flow reactor, either 3 reactors, 4 reactors, or 5 reactors, or big reactor or a small reactor. If you have combinations, you can get the same conversion for a very less amount of volume. That is what I'm climbing now. Yeah, please, all of you, whether does it make sense what I'm talking? Please, one of you can give. What I'm telling you is, instead of one reactor, if I go for a combination of reactors, your volume requirement will be still lesser. That is what I'm trying to show now. It may be surprising to you. It is true. It is true that instead of, because if you compare these two, plug flow is better for a positive order. But even plug flow, instead of plug flow, you can go, instead of one big plug flow, you can have one small plug flow and one small CSTR. It will give you the same performance for a much lesser volume of the reactor it is required. So generally, more the volume of the reactor, more will be the capital cost, and less will be your profit. If you are aiming for a profit, then you always go for volume less. You always want to have volume less because it occupies less space and it occupies less capital cost. So your what do you call profit will increase. Okay. Does it make sense what I'm talking? Yeah, some of you can give the feedback before I reveal what is better in this. Yeah. Anyone? No one. So you want me to name someone else, right? Let me not name. So I'll try to reveal now, right? Still, I didn't tell why this plug flow reactor is better, right? I'm still holding that. Instead of telling that, I'm just claiming that plug flow is better. But instead of plug flow, again, still there is a lot of combinations which are better. Yeah, please try to listen carefully. Here onwards, it becomes all Vitlacharya movies only. This becomes that, that becomes this. There is a director, you know, Vitlacharya, the Jagan Mohini or some names where hero becomes cat, cat becomes dog, dog becomes heroine, like that. Hmm? I don't know whether you saw it. He's a great director. In 70s, 80s itself, all this Bahubali, what do you call, gimmicks and all, what they did. He did with the camera itself, not with the computer. He's a great genius, Vitlacharya, one great director. In Tamil also, he took a lot of movies. In Telugu also he took. He's a Kannada person, but he took a lot of movies in Telugu and even Tamil. It may be dubbed in Tamil or something like that. The hero will not be like a hero. Hero is only some part it will be hero. Then he becomes dog, cat, or something like that. And heroine again will be like a snake or something like that. Right? Okay. This is going to become like that now. So please listen carefully. Each and every point is important. Right? Right? So let me go back to that slide, or let you can have this itself. This is the same derivation I'm showing you in the previous 11th full book I showed, the same derivation and same thing for epsilon a 0 and n is 1 and n is 2. N order is 2, you get xa by 1 minus xa and xa by 1 minus xa here square and here it is. Whereas for 1, you get ln down and xa by 1 minus xa in the top, right? So this curve also I showed. This curve also I showed. From this, we can tell that for any positive orders, definitely your volume required for CSTR is much greater than the plug flow reactor. Why it is like that, I still hold, right? I don't want to reveal that. I'll just reveal during the third unit, right? In the meantime, you can just have your own answers and we can have discussion. Now let us have this multiple reactors in series. So I just claimed that instead of one reactor, the volume required for a multiple if you go for a multiple reactors, that is reactors in series. Again, I repeat to you, reaction is same one. It is not a series or a parallel reaction. Reaction is A gives R, whereas the reactors is the series or parallel, right? In the next case, we can see even multiple reactors also. That is in the third unit, right? So I will go for this multiple reactors in series. So I'm going multiple reactors in series. Let us first put PFR in series or parallel. This is what I'm claiming here. This is PFRs in series, or PFR you can put as a parallel also. That's up to you, one over the other, right? So let us do with a series of this and a series of this, the other one, right? This you will do later. So all combinations is very much important. You get different derivations now. We'll do the derivation now. So we are assuming that CSTR in series, and I'm assuming that the volume required for all the reactors, let n reactors are there. So V1, V2, V3 till Vn. Let us assume that it can have a volume, same volume, or it can have a different volume. If the volume is going to be same, then V1 is equal to V2 is equal to Vi is equal to Vn is equal to V, capital V. There can be a same volume of plug flow reactors or different volumes of plug flow reactors also. Let us use the same volume. We know that F naught is the flow rate of first reactor. F1 is the flow rate which is coming out from the first reactor. That is going as an inlet to the first reactor. F2 is the flow rate to the second reactor, third reactor, like that. Let X conversion is 0 here. Initially, there is no conversion. The reactants are passing through this reactor. So there will be some conversion in the volume in this reactor. So let X1 be the conversion which is coming out from the reactor 1. And X1 is the inlet conversion to the second reactor. Like that, it goes on X2, Xi, and Xn. What else is there? The flow is taking in this direction, that is towards the right side. So for a ith reactor, let us do a material balance for this ith reactor. So ith reactor, let us put this reactor first. For this reactor, what is the, for first reactor, what is the flow rate? F0. For a second reactor, what will be the flow rate? F1. For ith reactor, what will be the flow rate? Vi by F0. That is the volume. Vi, V1, V2, V3, Vi by F0. This is the initial flow rate. Is nothing but integral, which is going from that. One second. Sir, வணக்கம் சார், சொல்லுங்க சார். டிபார்ட்மெண்ட்ல சார் 5 நாள் லீவ் எடுத்துட்டு இன்னைக்கு தான் வரேன். இதாச்சு, அதனால லீவ். ஆமா ஆமா. அதெல்லாம் வீட்ல தான் சார், வீட்ல அவங்க அம்மா கொண்டு அதுக்கு முன்னாடி ஃபங்க்ஷன் கண்டக்ட் பண்ணிட்டோம். நாங்க முன்னாடி 11 இயர்ஸ்க்கே பண்ணோம். இந்த டைம் எங்குமே எதுவுமே பண்ணோம். அதுல பிஸியா இருந்தாங்க. ஆமா சார், இப்போ இன்னும் இருக்காரு. அப்பா அம்மா அவங்க தாத்தா இருப்பாங்க. எதுல நாங்க இந்த இதுதான் ஃபங்க்ஷன் வைக்கணும். முன்னாடியே நாங்க 11 இயர்ஸ் ஃபங்க்ஷன் இருக்கோம். எதுவுமே இந்த டைம் இருக்குல்ல. உங்களுக்கு போட்டுருவேன். நான் கிளாஸ் முடிச்சுட்டு போட்டுருவேன். எவ்வளோ சார் நான் பண்ணுறேன். நான் ஒரு 1 hour. ஓகே, நான் போடுறேன். கிளாஸ் இருக்கேன், நான் போடுறேன். 10:30க்கு எடுத்துட்டு 11 o'clock. Sorry, in between call. Okay, what I am talking here, yeah, this for ith reactor, Vi by F0. Vi is the volume of it, by F0 is the initial. Is what will be the integral? For a first reactor, it will be 0 to 1, right? For ith reactor, it will be I minus 1 because I, right? You understood here? Generally, if you are putting this particular thing, then it will be 0 to 1, x0 to x1. So like that, for ith reactor, I minus 1 to xi, dxa by minus RA, correct? Is it correct? This is for all the reactors. This is for, you can put I as 0, 1, 2 till nth reactor. So this is having one volume, this is having one volume, this is having one volume, this is having one volume. So for n reactors in series, what will happen? Let you assume that all the V's, V1, V2, V3, V4 is equal to the total V, that is the volume of the reactor, VA. V by F0 is integral. This integral is there, right? You can eliminate this integral. Integral is nothing but summation. So sum of I to 1 to n, Vi by F0. What is Vi? That is what Vi. So if you substitute I as 1, then will be V1 by F0, then V2 by F0, V3 by F0, Vn by F0. And if you can add all that, you will get the entire volume of the reactors, correct? So that is nothing but V. Capital V is the entire volume, is nothing but V by F0 is V1 plus V2 plus V3 till Vn divided by F0. So this is on this side. What is on the RHS? Integral 0 to x xi minus 1 to xi dxa by minus RA. So you substitute I as 0, I as 1. If I substitute I as 1, then what will happen for first one? X0 to X1, correct? If I is equal to 2, then what will happen? X1 to X2. If I is equal to n, xn minus 1 to xn dxa by minus RE, right? What will happen to this integral? What will happen to this integral? So integral, this is same. Integral x0 to x1, here x1 to x2, xn minus 1 to xn. Before it, what it will have? Xn minus 2 to xn minus 1, correct? So you know that this integral is nothing but this upside integral is the downside. This upside integral is downside. This upside integral is downside. So you can cancel out all and you can put this to this. That is what I'm trying to climb. dxa by minus RA. What does this tell? What does this tell? This is V by F naught. V by F naught. What does this tell? Yeah, anyone can give this answer. Instead of single small reactors in series, I can you can calculate the performance here. The performance is equal to same as if you replace these reactors by one big PFR of having a volume of V, it will give you the same conversion. You add all this, you calculate this, it is going to be the same. Does it make sense? N number of PFRs in series, you can eliminate all the PFRs in series and you can put one reactor. The reactor volume should be equal to the sum of the volumes of individual reactors. That is what is this. This is only for PFR, right? Either the volume can be same or volume can be different or whatever it is. So you calculate the volume here, you calculate the volume here, you calculate the volume here, you calculate the volume. Let the volume is around 50 here, 50 here, 50 here, and 50. Some 4 reactors in having a volume of 50 each. Then what will be the volume? 200 liters. So you can eliminate these 4 reactors in series by putting one reactor having a 200 liters of volume. The conversion is going to be the same for the same flow rate. Okay. This is for series. You can do parallel also. Let us let us hold this parallel for some more time. Let us do the series for mixed reactors also. Yeah, I like to have some feedback here. Is it okay? Yeah.
Yes, sir.
Can we go for CSTRs? CSTRs will be a bit not the same as like this because you get something else. Can we go for CSTR now? Now see. This is the CSTR. We are having some n CSTRs in series. We are assuming that equal sized. So V1 tau 1 is equal to V2 tau 2 is equal to Vi tau I is equal to Vn tau 1, right? So all the, again, you can have equal sized or unequal sized. Unequal sized will be a bit difficult. So let us compare first equal sized. So again, this is the inlet to the first reactor. The outlet to the first reactor is set as an inlet to the second reactor. Like that, it goes on. So inlet is C0. Yeah, I'm putting C0 only. I'm not putting CA0. Any reactor, any reaction, C0 is the initial concentration. X0 is the conversion, is 0 initially. F0 is the flow rate. V0 or V is the volumetric flow rate. V1 is the volume of this reactor. Tau 1 is the space time in this reactor. So the outlet from it is C1 or CA1. If you are assuming it is A gives some product, then you can put CA1 also. So for any type of reactor, that is why I'm putting C1, C0, C1. The conversion here it is X1. that will go as an inlet to the second reactor, which is having a volume of V2 and tau as tau2. The outlet from the second reactor, let you are having a conversion concentration of C2 and X2 is the conversion. Like that it goes on. For a ith reactor, what will be the conversion and the concentration? You can see here. For a second reactor, your input is C1 and X1, the one less, right? Outlet is same, C2, X2. So like that for ith reactor, your conversion will be Xi minus 1. For a concentration will be I minus 1. And outlet is Ci and Xi. For nth reactor, it will be Cn minus 1, Xn minus 1, Cn, Xn, and V. V is the volumetric flow rate. Don't confuse with this V and this V. This you are writing as, that is why V naught or something like that I told you to write. So that nu or something like this they will write. This is V, normal capital, right? So don't get confused. That is why in our discussions we told it is V naught. V naught is the flow rate. That's what volumetric flow rate, right? It's up to you how you want to name it. So you have these notations. Any doubt in the notations? Then what we do? We go for a component balance or material balance for ith reactor. Let us put this particular reactor, ith reactor. Let us put the material balance. You know tau I. Tau I is nothing but, you know the term. For a CSTR, what is the expression? For a CSTR, what is the expression, ma? What is the expression? Tau by C naught or C naught is P by F naught or F naught is XA by minus RA, right? This is the expression. So we are comparing only these two. We are comparing only the taus, or you can compare volumes also. That's up to you. So tau of ith reactor, tau I by C naught. That is what we are climbing. C naught is Xi in the sense, what is the conversion here? Xi minus Xi minus 1, because earlier you are getting XAF because XAF minus XA0. XA0 is 0. That is why you are left with XAF or XA. So you have to write final minus initial. What is the final? Xi minus initial is Xi minus 1. Xi minus 1 divided by minus RA I. I is the nothing but the at this particular in this particular reaction, what is the rate? Now consider n is 1 and epsilon is 0. N is 1 in the sense the order is 1 and epsilon, that is nothing but liquid phase reactions we are assuming. If it is a gas phase, again it becomes difficult. Your expression is going to be huge. So for a comparison, we are using a simplest case of order is 1 and epsilon is 0. Then what will happen is your expressions, everything will become very short. Then you can compare. This is just for a comparison only. So for a simple case, for a first order and epsilon 0, we can substitute this minus RA as K into Ci. Tau I by C naught is Xi is nothing but 1 minus Ci by C naught. This particular thing is 1 minus Ci minus 1 by C naught, correct? You can write X in terms of concentrations, because you know that Ca is Ca naught minus Ca is Ca naught into 1 minus Xa. From this we can write Xa as 1 minus Ca by Ca naught. That is what I'm just trying here. I'm writing in terms of i's instead of A. I'm writing for anything. That is why I'm putting i's, right? 1 minus Ci by C naught minus 1 minus Ci minus 1 by C naught. That is for before the reactor, and this is for the ith reactor. So if you do that, this minus 1 and this plus 1 get cancelled out. Correct? You are left with minus Ci by C naught plus this minus into minus becomes plus Ci minus 1 by C naught. So this C naught get cancelled out. So you're left with Ci minus 1 minus Ci by K into Ci. This Ci gets cancelled out. Am I right? because Ci comes down, the C0 get cancelled out, K into Ci. Now you can write, sorry, Ci minus 1 by Ci. You can just take LCM of this. A minus B by B is nothing. A minus B by C is nothing but A by C minus B by C. So if you do that, then what will happen? Ci minus 1 by Ci is nothing but 1 plus K tau I. You can just take LCM here, get all the C terms to one side, get all the Ci terms to one side and divide one over the other. This is a very important expression. That is what we are getting. K tau I is the Damkohler number, 1 plus Damkohler number. That is what earlier also we claimed for a first order reaction. But here you are writing in terms of I, right? Is it correct? This is for CSTR, right? Now for constant volume reactors, your tau becomes T. That is, the space time becomes the average time inside. For all equal size reactions of volume Vi, you are left with C0 by Cn is 1 minus Xa by N. So C0 by Cn, you can write as C by C1, C1 by C2, Cn minus 1 by Cn. So what cancel out? This cancel out, this and this cancel out. So you're left with C0 by Cn. C0 by Cn is nothing but 1 minus Xan is nothing but you are having different 1 plus Xai K tau I for each reactor. Like that you are having N reactors, you are multiplying that. So it becomes N. So if you rearrange this equation, we want N. So tau for N order reactant is N into tau I is nothing but this from this equation. If N is going to be infinite, that is a lot of reactors are there in series. Here N is not the order, small n is only the order. This is capital N, the number of reactors. If there is infinite number of reactors, then what will happen is this equation reduces to this. This is nothing but a plug flow reactor. It's surprising. This reactor, if you put N as infinite and do this, what do you call simplification, you are left with tau N is 1 by K ln C0 by C. This is nothing but a plug flow reactor. C0 by C is nothing but 1 minus Xa because C is C0 into 1 minus Xa. So C0 cancels minus ln 1 minus Xa. That is what you get. That is nothing but a PFR in PFR. So what does this tell is equal MFRs in series. If you are having infinite number of MFRs in series of volume V1, V2, V3 or same volume, you can eliminate the entire thing and keep one CSTR, sorry, one PFR having the volume is equal to the sum of the volumes of this. Let it be 50, 50, 50 like that. Some 4 reactors or 5 reactors. Then what will happen? You can eliminate this particular thing by one PFR having a volume of 250 liters, the sum of this particular thing. It's a very important thing. So we got 2 reactors now. Reactors in series of plug flow reactor can be eliminated and then put one plug flow reactor of the same volume or volume equal to the sum of the volumes, or same equal size reactors, mixed reactor, you can eliminate by putting one PFR only, which will have your space requirement also very less. But the same volume is going to be the same. Yeah, I stop here. I think it is already time. I don't know it makes sense or not. You have to tell me. But this is different again. Unequal size reactors, one big reactor, one small reactor, one more small reactor. This will be entirely different than equal sized. Equal sized is much easier. Unequal size because your rate also will change. Because volume is changing, rate also will change. But here the volume is same, therefore you can have the same rate. But here it's not like that. So this complicated thing we'll see in the next class. Yeah, some feedback. Is it
Is it what do you call boring, or what does you tell? Yeah. Again, I tell you, CRE becomes very interesting if you are understanding. CRE becomes very boring if you are not able to understand. Did it? I'm talking with some sense or not to you? You have to feel that. Yeah. If you are not feeling, then this becomes a Vitlacharya movie. That becomes this. This becomes that. If there is a volume, different volume, then still it will be complicated. For the same simple reaction A gives R. If there is a complicated reactions, again complicated reactor systems, it becomes still difficult. Now you understood how big the topic is going to be. Is that okay? Yeah, I stop here. I think I stopped the recording. Yeah.